For this part of the video, we'll look at electric potential, not electric potential energy, just the potential, which is how much energy you have per coulomb of charge. That's pretty much what it means. The amount of work done that you need to bring a positive charge to that field. Here is a field right now. This is a positive charge in the middle. This is Q. He has a field pointing outwards. And if I had another test charge sitting right here, just chilling, and I will bring him closer. I will push him, push. He does not want to come. I need to do some work. So there is some energy required, okay? And depending on what his charge is, in this case it's a proton, I will divide that work by how much coulombs of charge that we have. So I know what my potential will be. I know what I will need to use. So I am going from A to B, for example. There will be two different potentials. I have a potential at A and a different potential at B. The closer I get, the higher my potential will be. So if I was to have like this here, and then I had this here, and let's say this was 12 volts, and let's say this was 0 volts, and we had a field line. The closer I get to the 12, the more potential is. The more I get to the right, the less potential I have. Same idea. This will stretch all the way to infinity. Eventually you'll get to 0. But here this might be plus 1,000, 1 million. It could be 12 volts here. It could be anything really. The potential here could be very high. And that means I will have to use that when I'm moving a charge closer to it. It depends on the charge that is causing it. I am not going to include the charge on the test charge. We're going to assume that there is nothing. We're only interested in the main charge, the field that he is in. This charge is sitting inside his field. So he will feel a force from him. He will have an energy from him. He is working on his different potential levels or potential lines, depending on what radius I choose to use. Okay, so the field, the potential will get closer. That means you will get a stronger potential as I get closer to it. We can use the rule like I mentioned, V equals U over Q, or the work done over Q. This rule stays the same. This is again just W equals QV from before. You would have done this before when you were doing charges and electricity. Work done is Q times V. It's the same rule that we're applying now in grade 12. So if you want to find the potential, simply use this rule. Whatever energy that he would have, divide by the charge itself. If I had 100 joules of energy and I had 2 coulombs of charge, the potential there is 50. That's, in this case, will be volts. That's just a quick mini example there for you. And electric potential difference is when I change the potential energy. I will move the charge between the 2 points. Like I mentioned, if I had a B and then I had A, this is B, I'm quickly drawing it, this is A, and I move between them, I move closer, I am now doing work, I am having to move it closer, I can calculate the energy change, I can do all that. It will be the difference between whatever potential this is. Let's say this was 10 volts and this was 5 volts. The difference between them, yeah? In this case it would be 5. So that is really important to know. VB minus VA, or I should actually easily say V final minus V initial. That's the better way to say it. Final minus initial. Or the change in work, or the change in energy, divided by Q, which is the charge. So we can see that the electric potential is always decreasing in the direction of the field. So if the field, this is a positive charge, the field line is going out. You can see that this field, this is 10 volts, this is 5 volts. Further away I get will be 3 volts, 2 volts, 1, and so on. It will decrease the further away I get from the positive charge. Very nice. Formula right here, V final minus V initial. Checking this out, a proton will move towards the negative charge. So if he moves that way, we'll do minus 2, minus 10, which means he lost 12 volts. That makes sense because he wants to be here. The positive charge wants to be here, so he will lose potential. So that makes sense. Easy peasy. So negative potential difference, as we've mentioned, there's another example, between 10 to 6. We will take the positive charge and we will move him down towards the negative charge. So I will do final minus initial, 6 minus 10, negative 4. He lost 4 volts coming down. And if it was the other way around, if I take this positive charge and I moved him up, what you'll do is final minus initial, in this case 10 minus 6 again, and this time it will be positive 4. He gained 4 volts of potential, which makes sense because he wants to repel. He does not like these positive charges. He will repel by them. He will need more energy, which is why the potential has increased. So potential is basically like voltage, potential energy is energy, funnily enough. Okay, however, if I had a point where I was sitting and I moved along and my radius didn't change, if I stayed in this area with my radius being the no change, you will find that there will be no work done. It's easy because there is no change in potential. I am not getting closer, I am not getting further, I am staying in my same line, which means on an equipotential surface, the potential is equal. So if I had 10 volts here, this whole thing is 10 volts. This whole line is 10 volts. I did not change it. If I do V finals minus V initial, it'll be 10 minus 10, you'll end up with 0. 0 work done. No work done on an equipotential line. So if I used parallel plates, as I drew earlier for you, it's uniform in the center, but not in the side. So we will ignore the sides. All our calculations will be assuming here somewhere in the middle. That's what we will do. So the distance we would say is D. So from here to here, we will call it D. And this is going to help us really get a new formula. We already know V final minus V initial. If I know that, that is nice and easy. For example, or that could be VI, that could be VF. I can call it 10 volts. I can call it 5 volts. It doesn't matter what's going on if I have it. However, I might not have it. I can find it by using the VED formula. V equals ED. The electric field is the change in potential divided by the distance. So I can just call it VED. And of course, QV. These are the 3 formulas you will want when you see parallel plates like this. We will use these 3 formulas in this situation. However, if we go back to the point charge, your formula will not be just as easy, because as you get further out, the field gets weaker. It's not a uniform field anymore. The directions are changing and the strength is changing. So as I'm moving between A and B, I will not simply be able to use VED, for example, because the potential changes as I get further away, gets weaker. So what you're going to do is we can use a formula and we can use an integration to derive a new formula. However, as it seems, we might not need to do all of that. So you do not need to memorize this. But if I was to start with VED, I can do the integral between A and B of ED. I'll call it dr, r as in radius. And instead of writing E, I will just write kq over r squared. Remember in the previous video I mentioned to you, the electric field is kq over r squared multiplied by dr. We're only changing the distance, so we can take the k and the q out of this. We're only integrating in terms of the distance. So that'll just leave me with 1 over r squared. And if I'm dividing by r squared, we'll keep it as minus 2. It makes it easier for us to do the integration. So when you integrate that, we will get negative r minus 1. Yeah, raising the power, multiply by the power. And remove the negative by flipping the A and B. So this is B to A. Swap this around from A to B. That means it will become the positive side. That's r minus 1. Or we can bring it back to the beginning again, 1 over r. So if you put that into the 2 positions at B and at A, or A and at B, same thing. So we'll have kq 1 over A minus 1 over B, because this is 1 over r. That is the rule that we will stop at. This is what you can use to find the V at 2 different locations around a point charge. So this is for a point charge, not for 2 plates. Okay, so that will help us find this easily. You may have to differentiate. I did do an example with you, and I remember I asked you if this was negative, and we realized as you're getting further away, you will decrease your potential. So we have a little negative here. Give you an example with this one, x squared, xy squared, yz. You have to find using the coordinates, and this was the x and the y and the z coordinate. So you have to differentiate in terms of x, differentiate in terms of y, and differentiate in terms of z. And when we solve this one together, when we differentiate for this, we bring the power down, then you take 1 off, you will get 2x, and then you do the same thing here. the x just disappears, and then there's nothing over here. So that leaves me with x, 2x plus y squared, because x is gone. And then once you've done it for x, you will do the same thing for the y, differentiate for y, there is nothing here. So bring that 2 down, 2xy, take a power off, 2xy. Over here, the y disappears, leaving only the z, done. And when I'm differentiating in terms of z, nothing, nothing, and well, that disappears, y, easy. Then what we do, substitute. We substitute the numbers in. Take our formula, and we will substitute, put the numbers in, x, y, and z coordinates, and then you have your final answer here. And that we can stop there. That's all you need to do. I doubt it will come, but there it is, just in case. So we've learned a few things. We've learned the potential energy in a system of charges. We know the work done to move it. We know the electric potential, energy per coulomb, and a potential difference when you move it, so the change in potential. Next, you need to find the potential at any point around multiple charges, more than one. For example, here, 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 and here. For these charges, you have to find the potential where it would be 0. We know this is positive, so maybe this is plus 10. Maybe this is also plus 10. Maybe this is minus 10. Maybe this is minus 10. So going from here to here, going towards this way, it will decrease up to about maybe here. So this might be 9, 8, 7, 6, 5. But then it gets bigger again because this is positive. This becomes 6, 7, 8, 9, back to 10 again. It will never become 0. It will stay on the positive side. Same thing at the bottom over here. And this will be minus 9, minus 8, minus 7. It'll get weaker and weaker and weaker, but it'll get stronger again. This will be minus 9, minus 8, minus 7. And it will never get 0 here because it will pick up the strength. Between here and here is when it matters. If I'm going down this way, this direction right now, yes, I will cross the 0. 9, 8, 7, 6, 5, 4, 3, 2, 1. 0, minus 1, minus 2, minus 3. Because to get from positive 10 to negative 10, of course, you have to cross the 0. Same thing over here. If I'm at plus 10 over here, and this is minus 10 volts over here, I must cross by 0. It doesn't even have to be 10. It could be 1, minus 1, plus 1. I still need to cross 0 in between. And even here as well. This will be also the same thing. So this will become an equipotential line of 0 volts. So these three are the correct answer. Easy peasy. B. Multiple charges, we'll use the superposition principle again. So what we can do is we can add all the individual voltages. I just need to charge my laptop before the battery dies. Add them all up. We can use the KQ over R. So KQ over R1, KQ over R2, Q over R3. So the key point in this one is for the voltage, for the potential, we only do KQ over R. We do not multiply these together on these together. That is only for the energy. If we're at a point, at a position P, for example, over here, we have to do Q over R, Q over R, Q over R, and add. Or subtract if one of them was negative, by the way, in this case here. So in order to find this one, we can do V plus V, K Q over R, K Q over R. We have the two radiuses here. That's nice and easy. Put the numbers in. 9 times 10 to the 9 times 1 over this 0.5 plus 9 times 10 to the 9 multiplied by negative 2. They made the minus here, so that will turn this into a minus. So they put the minus there instead. Same thing. And you put the numbers together, add them up, plus minus obviously becomes minus. And your answer is overall negative, which means this one is much stronger. He feels a stronger force, which makes sense. The distance is the same, but his Q is bigger. I've increased the Q, which means the V will be bigger. That's another concept you must be able to understand as well. And there you go. You now have the potential there. Easy. And if you want to find the potential difference between something that's moved, like for example the bigger formula I showed you, the one that we integrated to get, there's my VA and VB. This is not a constant voltage or a constant potential. It will get weaker as we go, so we have to use the integral formula that we did. KQ 1 over R final minus 1 over R initial. So if I'm moving from A to B or from B to A, it's really important. So if I start with A to B, A is my initial and B is my final. If I move from B to A, then of course B is my initial and A is my final. So make sure you get them in the right way. Initially we will start from A to B. This is final, this is initial. I think when I solved it with you I did it the other way around. So here we go, initial and final, fixed it now. And K, 9 times 10 to the 9, and we're going to multiply by 1.6 times 10 to the minus 6, this is the Q, and we will do 1 over R final, 1 over R initial, so the initial distance and the final distance. Subtract them, get your answer A to B, and if you were to get the other way around, you will just have the opposite sign. So if this was -2, this one obviously will be +2, or in this case -20, this will be +20, because I'm going the other direction. All the numbers stay the same, I've just changed the direction. Here's a summary then. Potential energy, KQ1, Q2 over R squared. 3 or more points, you add all the points together. You like Q1, Q2, Q2, Q3, Q1, Q3. Potential is KQ over R. At the 3 points, you just add them again. KQ1 over R, Q2 over R, Q3 over R. That's all you need to do for that. Thank you.